everyone, welcome to lecture 4.3, the definite integral. So today we're going to be talking about the definite integral. Last time we talked about Riemann sums, and we're going to see the definite integral is the same thing as a Riemann sum, basically. Just we're going to see that we can think of it as a sort of its own object, and we don't always have to connect it directly to the Riemann sum thing that we did last time. So let's remember what we were doing with Riemann sums was we were starting with a function, maybe something that looks like this, and we were approximating the area under the function, right? So we imagined taking, like, so the function starts here at some point a, and it goes all the way to this x value b, and I can imagine shading in exactly the area between a and b under the function. We talked about how if this original function is representing something like velocity, then this area is representing something like the total change in position of the object. So we have some physics reasons to think about these kinds of areas under curves. The basic idea we had with Riemann sums was to, instead of kind of trying to get the area, this continuous sort of smooth area to start with, we imagined breaking it up into a bunch of rectangles first. And my drawing's not great, but we made them the same size, the same width, and I call that width delta x. That's like the width of one of the rectangles. And we had this number n, which was the number of rectangles. This was the width of a rectangle. And we have this kind of formula-looking thing for adding up a bunch of these rectangles, right? Each rectangle has a height, which is given by the function value, basically. So like if we're at this function value, say I'm doing a left Riemann sum, then this would be the height of that rectangle. And if I called this position, maybe x2 or something, then the height here would be f of x2. And since the width is delta x, the area of that one rectangle is fx2, the height, times whatever the width is, delta x. So that's one rectangle. We talked about using the symbol xi to stand for generic rectangle. So this rectangle, number 0, rectangle number 1, rectangle number 2, etc. Or sorry, well, the position on the axis corresponding to that rectangle. So rectangle number 0 maybe starts at position x0. And so evaluating the height of the function at all these different x values, so that's this, and then multiplying by the width, that's the area of rectangle number I, and then if we add them all up, that's the sum of the areas of all the rectangles. And we said I goes from 0 to n, meaning I'm adding up rectangle number 0 all the way up to rectangle number n. So yeah, so that was our basic idea. Last time we had a fixed value of n. By the way, I said that with a left sum, this sort of should be n minus 1. So for a left sum, and then for a right sum, it should be I equals 0, or 1, not 0, 1 to n. And then the same thing here. So that's because, right, imagine like breaking this into 3 rectangles, n is 3 in this picture. I'd call this x0, this x1, this x2, this x3. So depending on the left or right, we're kind of using only some of the values, either using the left endpoints or using the right endpoints. Not a huge deal, I just noticed that I wrote n, and then up here I have n. We will see in a minute that it's not going to actually matter too much, but just in case that was confusing. Okay, so last time we did this all for a fixed number of rectangles, right? We said 3 rectangles, or 4 rectangles, or 10 rectangles. So the whole kind of idea we started with was, well, if I have a small number of rectangles, maybe I'll do 2 rectangles to start with. approximating my function. That's a pretty weak approximation, but it's a good start. And if I move on to maybe 3 rectangles, it's a little bit better of an approximation. And you can imagine if I do, more and more and more and more rectangles, finer and finer grained approximation, and it's looking like it's, really maybe approaching that sort of actual smooth, continuous area under the curve. If I had maybe like an infinite number of rectangles, question mark. So we kind of want to think of the area under the curve, like I want to think of it as the entire shaded thing, like all the way. And I kind of want to think of that as like an infinite number of rectangles, and like having this n here be infinity. You have to be a little bit careful, and actually, well, yeah, so if we think about this for a second, like what does it mean to have an infinite number of rectangles for some of the things we were talking about, right? Like, first of all, if I had an infinite number of rectangles, I'd have, an infinite number of these xi's, and which is maybe okay, but I'd be adding up like an infinite number of these function values, right? Which, when we have a finite number of them, it's not that weird, right? We just like, oh, height 1, height 2, height 1, height 2, height 1.5, whatever, it's fine. But if we're adding up an infinite number of y values, it's kind of like unclear if that's like going to make sense, right? Like maybe, like if these were all the y value 1, for example, like if our function was just y equals 1, right? If I'm adding up an infinite number, so say for a is here and b is here, if I was adding up an infinite number of 1s, that's probably like infinity or something, right? There's another problem, which is the plan after adding up all these y values is to multiply it all by delta x, or alternatively, you can think of multiplying delta x by each one. That's the same thing. But if we have an infinite number of rectangles, what is delta x, right? I told you that delta x was b minus a divided by n, where n was the number of rectangles. But if I have an infinite number of rectangles, that's pretty weird, because now it's saying let's take this finite distance between a and b divided by like infinity. That seems like it should be 0, maybe, if this is going to infinity. So there's kind of two things happening, right? Adding up the heights seems like it's going to infinity. Doing a division to figure out the width of the rectangle feels like it's going to 0. So this is not a obvious thing to resolve, an obvious paradox to resolve. People have been thinking about these ideas of adding up infinite things and maybe dividing by infinite things for a long time. Like if you've ever heard of Zeno's paradox and other similar things, like the Greeks and other philosophers and stuff were thinking about even thousands of years ago, are kind of to do with all these exact ideas. Like Zeno's paradox is, how do I get all the way there if I first have to go halfway there? And before doing that, I have to go halfway to the halfway point, etc. So it's not super obvious how to resolve these things. So, we'll have an answer, but I want to kind of emphasize that it's sort of a big deal. It took, people came up with calculus 200 or 300 years ago. That was the first time people really figured out a useful way to resolve these problems. So basically how we're going to resolve this problem is to not treat these two things as separate, right? It's not that I'm adding up infinite number of y values and then dividing them by 0 or an infinitely small thing or something like that. I'm doing it one rectangle at a time, right? I'm going to have some y value. As when I have more and more rectangles, this is, for any given rectangle, as long as for a given rectangle this is a finite number, then as n gets bigger, this delta x is going to get smaller. But it's kind of it's kind of like if I have the same height thing, but like if I have more rectangles, but each one is half as wide as they were before. Like if I double my number of rectangles, but cut their width in half, right? Then I still maybe have the same area, is sort of the idea, right? Let's say I have 2 rectangles. If I imagine doubling the number of rectangles, I'm getting my, remember I have my function, I'm getting like my better approximation. I'm doubling the number of rectangles, so on some level I'm doubling the number of things I'm adding up, but also these rectangles are half as wide, right? So I'm doubling the number of things that I'm adding up, but the size of the things I'm adding up is also sort of getting cut in half. So it turns out that this like adding up to infinity and this dividing by bigger and bigger things end up like balancing each other out in just the right way for it to make sense to say that this approaches a nice smooth area. So I might say like colloquially sometimes that like we kind of imagining going to an infinitely thin rectangle, and if we can add up all these infinitely thin rectangles, that gets you the area under here. That's sort of a short, not quite true, but short way of saying this chain of reasoning here, where at each finite stage of this process, I have a finite number, which is its total area, and yeah, as I get more rectangles, the number of rectangles maybe gets bigger, but also their widths also get smaller at the same time, and that's going to balance out enough to make sense. So we're not going to be too concerned, like in this class, of like doing, like I want you to understand this kind of idea, like philosophically. I think it's interesting. We're going to use most of what this class is using sort of math technology that people came up with after thinking really hard about some of these ideas. So our first step in that direction is this thing called the definite integral. So we already had our Riemann sum, which was like this, and now I'm going to write limit in front of it. So right, what this means is that here's an expression. It depends on n, right? So this is the area under my curve when I have a specific number n of rectangles. But when I write limit as n goes to infinity, that means sort of imagine the sequence you get, where first, if n is 2, I have 2 rectangles. Figure out what that Riemann sum is, figure out what the area is. Then go to 3 rectangles, n is 3. Compute that area. Then go to n is 4, compute that area. Then go to n is 5, compute that area. And then just keep going forever and sort of hope and pray that that actually becomes, sort of converges on a number. This is somewhat plausible, right? Like for example, if I take, well, so the idea of having this sequence which becomes a specific number is not that crazy, right? Like if I have the number 2, let's just try cutting it in half over and over. I get 1, 0, 0.5, sorry, not 1, 0. 2, 1, 0.5, 0.25, 0.125, 0.0625, etc. Like these numbers are getting closer and closer to the number 0. They never quite they never exactly hit the number 0, right? But they're getting closer and closer to 0. And you might remember from Calc 1, this limit idea says, when you have a situation like that, you sort of get to say, go all the way to 0, and like that's what the limit means. So I can make this 2 get as close as I want to 0 by just cutting in half enough times. And so we say that the limit of that process is the number 0. So in the same way here, I'm doing a Riemann sum with 10 rectangles, 100 rectangles, 1,000,000 rectangles, and I'm checking the area I get every single time. And if it looks like those area numbers are like, leveling out, approaching a particular number, then I say that the limit really is that number. That's a fine idea. The sort of hard part, if you're like inventing calculus, is like justifying that actually happens, right? That for like proving that actually, yeah, you do settle out to a finite number in a lot of cases, at least. So we're not going to do that so much, because that's pretty hard. If you're curious about that, that's kind of what more advanced math, like real analysis, graduate level stuff, is kind of about. Or ask me if you're curious. But basically, most functions that we're going to deal with, it works. And if it works, we say that the function is an integrable function, so it's possible to integrate it. So integrate is this word, basically, for doing this process. To go to an infinite number of rectangles and converge and approach a specific finite area number. You don't have to worry too much about this. Like I said, most functions we'll do with are integrable. And in fact, like, I don't know if I say this down below, but if your function is continuous on the range you're interested in, then it's integrable. Right? So any continuous function, for sure, this is going to work. The times it doesn't work is really like edge cases, pathological stuff that we're not going to worry too much about. 99% of the time in real life, like doing physics or engineering or something, your function is going to be continuous, and this concept is going to turn out to make sense. One thing about this notation, yeah, so that's the idea. So we do this Riemann sum idea, and we bundle that all up into a short notation, this notation on the left here, and let's just look at what each of the parts is. So first of all, there's this S symbol. I'd probably call it the integral sign, or the integral S, or something like that. It's just an S. It's like, historically, it was like a long S, and it just kind of got weird looking. It's maybe supposed to remind you of sigma, which is like the Greek letter for S. And sigma is kind of like a sharp, chunky, discrete sort of sum. And the S is like a nice, smooth thing, so kind of something you can help remember it. So yeah, that's the symbol, and this just is, it's indicating that we're going to do an integral. There's also this dx on the right side. So I will talk a bit more about the dx, but for the moment, just think of the dx on the right and this integral symbol on the left as sort of brackets around the inside. So when I see the integral symbol and the dx, that means, hey, I'm doing an integral. What function am I doing the integral to? I'm doing it to this one inside. That function is sometimes called the integrand, the thing you're integrating. So integral sign, dx, it's left and right brackets. And like, you're gonna be able to do like algebra moves. You're like, okay, what's the integral of x plus 1 dx? And like, you can imagine parentheses here. Like the 1 is not attached to the dx. And it's like, oh, that's the same as like x plus 2 minus 1 dx or whatever. Like, you can do algebra moves sort of inside the integral symbol. Okay. Then the other thing is the a and the b. So that's pretty self-explanatory. It's just the left and right endpoints of the integral you're looking at. Right? We're integrating we're doing our Riemann sum between a and b, integrating between a and b, and that matters, right? Like if I was doing 1 to 2, that'd be different than doing 2 to 5. Different part of the function. Okay. Since we're here, I will mention something about the dx. So I was talking this big story on the right side over here about what it really means to go to infinity. I mentioned that sometimes you can kind of think of the area under the curve as like, let's have an infinitely thin rectangle, and then imagine just adding up like all infinity of these infinitely thin rectangles. That is how people were first thinking about this historically. And before, like, it took a couple hundred years to like really figure out all this limit stuff to make it make sense. People were originally thinking about it in terms of an infinitely thin rectangle. And since delta x was like the width of one finite rectangle, they kind of imagined maybe dx is like the width of an infinitely thin rectangle. Now, like we said, the width of an infinitely thin rectangle should probably be 0, because it's like, take your delta x divided by n, and then let n go to infinity. It's probably 0, right? So, so maybe like dx is 0. So it's a little like not well defined the way it is, but it's the notation that people used and still use today. It is okay to think about it sometimes, right? Like, it can help you remember we're thinking about rectangles, right? Like, if I think this is like an infinitely thin rectangle, and then this is like the height at a point x, then the height at the point x, right, times the width of an infinitely thin rectangle is sort of like the infinitesimal area of that rectangle. Don't take it too seriously. In math class, at least. If you do physics, engineering, sometimes they do take that a little more seriously. But yeah, I would say just think of it as brackets around your integrand. Okay, one last comment here is that we talked about left sums, middle sums, and right sums. It turns out that as long as your function is integrable, meaning it's nice enough function that the integral is going to work out, this limit is going to exist, like if f is continuous, for example, then it actually doesn't matter whether you build this part using a left or right or a middle sum. Basically, the idea, right, is like as your number of rectangles gets larger and larger, like who cares whether I use the left side or the right side, right? If they're getting skinnier and skinnier, this kind of left and right in middle, they're all like getting closer to each other, and they're kind of just approaching this sort of single infinitely thin line. So yeah, in some classes, like in a more advanced class, you maybe be interested in proving that it doesn't matter. We're not going to worry too much about it. But yeah, so like you could write n here, or n minus 1, or even n minus 100. It all actually like technically means the same thing because your n is going to infinity, and it doesn't matter. The notation is a little bit funny because like this delta x also depends on n, so you have to be a little bit careful if you're doing it really carefully. Also just mention this xi star, because I'm not sure if I mentioned it yet. So oh no, I have not mentioned it yet because it's to do with this left, right, middle thing. The xi star just means the point I'm grabbing, the x value I'm grabbing to plug into f to become the y value, is some x value in the interval, the particular interval. Right? The star means it could be the left one, or the right value, or the middle value, or in fact any value within that particular interval. And I'm grabbing that x value to go into f to become the height of the function. Because it doesn't matter which you choose, if it's integrable, then this star is kind of not committing to which point you're taking. You don't have to worry about it. We can always just use just regular xi like we were doing before. Okay, one other thing I'll just caution right now is that if this sounds like kind of crazy, like doing this whole right hand side, it is pretty crazy, and it's kind of a lot of work to do, like to find areas of under functions by doing this whole limit sum Riemann thing on the right hand side. It's actually kind of a pain. So we will see very soon that there's actually a better way to do it, like a more efficient way to do it. And the fact that there is a more efficient way to do it is kind of the whole reason that this class even exists, and why no one cares about calculus, is that there's this kind of crazy like process to do on the right hand side in order to come up with this sort of nice like geometric thing on the left hand side, the area. And it turns out there's going to be a shortcut that will let us avoid actually doing the Riemann sum. But at this stage, we are still thinking about the Riemann sums, and we're going to do some examples where we do one completely by hand. Which is good to see the bones of it at least a couple times. Okay, so that's sort of the intro to what an integral is. I'm using this word, the definite integral. That definite is just a word that means, like, we have a's and b's here. We are actually finding the area under a function. We will see, yeah, I should have had like a's and b's here. We will see pretty soon that we're going to be writing stuff like this, where there's not a's and b's, and we're going to be calling this an indefinite integral, and I will talk later about what the differences are. But the definite integral is like, I'm really doing a geometry thing, I'm getting the area under the curve. Okay, so let's keep going. So we're going to try to do a Riemann sum completely by hand to compute this integral. So we're doing this function. It's y equals 2x minus 3. You don't really have to draw it, but I like just kind of having a feeling I know what's going on. So this is minus 3, it's going to start here, it has slope 2. So it's looking something like this. I can figure out what this point is if I care, but I don't really care. So we're integrating from 1 to 4. Actually, let's find this point just so I can draw the picture better. How do I know where this function is crossing the x-axis? Well, I gotta take my function. Yeah, this is equal to y, right? So when I'm on the x-axis, that's the time when y is 0. So I can just check what x must be in order to make y 0. And then that's just a little bit of algebra. Okay, x better be 3/2. Which I'm converting to 1.5, not because I particularly like the decimals, but because we're looking at the numbers 1 and 4 as our endpoints, and I want to know how, what this x value has to do with the number 1. So if I don't know, off the top of my head that 3/2 is bigger than 1, I can convert it to 1.5. So here's 1.5, which means 1 is like here. And again, it doesn't have to be like an accurate drawing, just schematically, 1 is to the left of 1.5, and 4 is to the right of 1.5. We are doing the area under this curve from 1 to 4. So remember, I keep saying area under the curve, but it's really area between the curve and the axis. So on the left side here, the curve is below the axis, so I'm doing this area sort of between the curve and then up to the axis. On the right side, the curve is above the axis, so I'm kind of doing this area below the curve and above the axis. So you'll see this is very common, right? If my function is going across, the integral is always going to look something like that. If it's going across this way, the integral might look something like that. Yeah, something like that. Okay. Okay, so that's just visually the area that we're going to get. Let's do our Riemann sums. So theoretically, the first step is to write down that this is equal to the limit as n goes to infinity of my Riemann sum, right? So I'll just write it. So it would be like f of xi delta x I 0 to n. F here is our function, our integrand. Right, so I'll say f of x is 2x minus 3. So the way this is going to work is we're going to basically think about this Riemann sum, the sum here, just like we did last lecture. So we'll work on that for a bit first, and then at the end we're going to take a limit. And we'll remember some kind of limit rules from calculus, Calc 1. Okay, so just like last time, what are the things we need? We need we need n. Here, n is not a fixed number. Like before, we had like n is 4 or n is 2 or something. Here, we're just having n is just n. It's just a variable. That's okay. You don't even need to write that, but it's just worth mentioning. What's delta x? Well, it's b minus a over n. B and a are our numbers here. A is 1 and b is 4. So I gotta do 4 minus 1 all over n. So 3 over n. And again, if n was a fixed number, like 2 or something, I'd have 3 over 2 right here. But it's okay to have it be a variable, 3 over n. We will see that this expression will end up having n's in it, which is fine, because the plan is to take a limit as n goes to infinity. So we want there to be variable n still in this expression on the right before we take our limit. Okay, what else do we need? We need the xi's, right? xi was always the left endpoint, a, plus I, the number of times I've jumped to the right by a size of delta x, I times delta x. We can plug in our numbers here. A is 1, I is I, and delta x is 3 over n. By the way, it's fine and common to rewrite this sort of like that. The I times a fraction is the same as I on the top of the fraction, so you can write it like that. Okay, so we just have to kind of assemble this into our sum. It's going to look like this. I'm going to have f of xi delta x. I'm going to skip writing the I equals 0 and the n. You should not be lazy like me, you should write them, but since it's not going to matter too much, I'll skip them for the moment. F of xi, so what does that mean? That means I've got to do f, and I have to plug in xi, which is this, 1 plus 3i over n. Delta x, what's that? It's 3 over n, so I put it 3 over n right here. Nice. And then, like I've said a couple times, we're not done here. We got to actually plug our xi into f. Or what's f? Come back here. F is 2x minus 3. It's the integrand, the thing we were trying to integrate. So, right? 2x minus 3 means, like, this is x. So this is my input. So everywhere there's an x showing up, I replace it with 1 plus 3i over n. So that'll look like 2x, x is 1 plus 3i over n, and then minus 3, right? So that's f of x, xi. I think it's a great idea to put this in parentheses, because I don't want to forget that when I'm multiplying by 3 over n over here, I'm not just hitting the 3, I'm hitting the whole thing, right? Okay, so that is basically our sum. The plan is to take a limit. So here is where it gets a little bit annoying. Remember, if I just ask you to set up a Riemann sum, like on the exam, I'll have questions probably, maybe, which say something like set up a Riemann sum. I'm just asking you to write this and to write limit as n goes to infinity out in front, and we'd be done. But for this lecture notes, at least, I wanted to show off what it would like to go all the way and actually get a number out of this. It's not going to be possible to just like immediately send n to infinity. So you might remember from Calc 1, right? If I do like limit as n goes to infinity of something, n squared plus 1, then I just evaluate it, right? I kind of imagine, typically, I'm like plugging in infinity to the variable. So like I say, okay, n is going to infinity, so that means n squared is going to infinity, so this is like infinity plus 1, so this is like infinity. But there's other situations where that doesn't happen. The most common one maybe is something like 1 over n plus 2, something like that. Now I say, okay, what happens when n goes to infinity? Well, when n goes to infinity, I'm having 1 divided by infinity, and really, I don't want to say 1 divided by infinity because you're not really plugging in infinity. You're really imagining a sequence. Like, okay, 1 divided by 1, okay, that's a number. Then 1 divided by 2, that's another number. 1 divided by 3, 1 divided by 4, 1 divided by 5, 1 divided by 6, 1 divided by 100, 1 divided by a million. So I'm imagining this like sequence of numbers, and I'm saying, does that number sequence approach something? And here, it looks an awful lot like it's approaching 0. There's a technical definition of approaching, which is basically I can get as close to 0 as I want as long as I pump n larger and larger. But basically, it's trending towards 0. So because of that, all that, I get to say that this part is going to 0. But then I still have this 2 left over. So this ends up just being 2. So sometimes the presence of an n and then n going to infinity means we end up with infinity. But sometimes there's an n which is maybe like in a fraction or something else that means that it ends up approaching a specific finite number. That's gonna be what happens here. Because our function's integrable, that means it's gonna work out. But it's not like super obvious how to like apply any of that to this expression right here. Right? I'm adding up an infinite number. Like the issue is like like here I had 2 terms that I'm adding. But here the number of terms that I'm adding depends on what n is. So it's kind of weird. Right? Like when n is 10, I'll have 10 terms. When n is 100, I'll have 100 terms. And yeah, maybe each term is getting smaller or something, but it's not super clear how to work with that. So it turns out the trick is going to be using all these sum properties that we talked about last time. So basically we will be able to break this apart into some smaller pieces, and some of those smaller pieces we will be able to turn into formulas that do not involve the sum symbol. So I won't have this increasing number of terms. And then we'll be able to do it. So let's just give that a shot. So if we scroll back for a minute to the previous lecture, remember what were some of these sum things we learned about. The main rules we're going to be using here is constant multiple rule. So I can pull, like here I can pull this 2 out in front, and I get this. We have this addition rule, where like if I'm summing something plus something, that's the sum of the first thing plus the sum of the second thing. And then the real kicker is going to be basically things like this and this. See, what's happening, right, is we're going to have stuff that looks maybe like this, like a sum with k's, and I'm going to be able to convert that into a formula which does not have the sum symbol. And I'm going to be able to take a limit here, right? N's going to go to infinity, and you know, in this particular one, that's going to go to infinity, but you know, we'll see what's going to happen. Okay, so you'll have to have these like on hand if you're doing this. And the most common one is this one. We get n times n plus 1 over 2 when we sum from 1 to n. So hopefully I can remember that without having to scroll back. Okay, so let's start breaking this apart. First of all, we can distribute this 3 over n inside. And I want to do that because it's going to make it 2 terms and just a little bit easier to work with. So I have 2 times 1 plus 3i over n, distributing in the 3 over n. So that's multiplied on the first term. And then minus 3 times 3 over n, that's multiplied on the second term. Let's just keep simplifying and stuff. So 2, let's just multiply the 2 through. So like this. 2 plus, so 2 times 3i over n, so that's 6i over n. We still have 3 over n out here. And then minus, this is going to be 9 over n. remember the 3 out in front is the same as multiplying by the 3 on top. Let's keep simplifying. I can multiply this 3 over n through, so I'm going to get 6 over n plus 18, I think, I over n squared. Yeah, so don't miss this, right? When I multiply it on the first term, it's just over n. When I multiply it on the second term, there's already an n there, so it's n times n on the bottom, so it's n squared. And then we have minus 9 over n out here. You can go ahead and combine the terms, right? These terms are like the same units. They're both something over n. So I can do 6 minus 9 of those, which is negative 3 over n. And then I also have this 18i over n squared. Great. So at this stage, we want to start pulling stuff in front of the sum symbol as much as we can. So, well, first of all, we can split this into 2. So that's one of our sum rules. I can split this into the sum of both of the parts. Now, this next step is going to be a little bit weird, but we can actually pull this whole thing here out in front. So before we saw an example where if it's like 2i, we can pull the 2 out. So it's 2 times sum of I. Because this 2 was like just a number, and the I was like the real variable. Like there's an I in the base, in the bound here. Here, right, we have I equals 1, equals 0 to n. So this n here, this n, it's not a variable. Like, it's not I. So only if it's an I are we prevented from pulling it out. Any other constant you can pull out. It's a little weird because there's also n up here, but it's actually fine because, like, this term, it depends on n, but it doesn't depend on I. And the stuff inside the sum symbol is like I is changing and maybe changing the stuff inside. But as I changes, right, we go from one term in the sum to the next term, this 3 over n thing, it's always 3 over n, right? At every single step of that sum is 3 over n. So we can actually pull this out in front. 3 over n, sum symbol. What's left, or sorry, negative 3 over n. What's left? Probably 1, right? So you have to think about that for a second, but like if I multiplied this back in, I would definitely get back to what I started, right? So when you pull something out, like pull it completely out, often there's a 1 left over. Okay, and then we still have this other term over here. And again, the I is the only part that has to stay inside because it's like the variable. But the 18 and the n squared are both like numbers which can come out. 18 can come out front, n squared can also come out front, kind of like on the bottom, because it's on the bottom of the fraction. I can actually just pull the fraction 18 over n squared all out front. So like that, and we still have the I inside. Okay, so it looks a little messy, but like we're kind of almost done actually. Just remember these are from 0 to n, 0 to n. So we just have to use our sum rules from above. One of our rules was that if I add up 1, right, this is 1 plus 1 plus 1 plus 1, for, you know, how many times? Well, if I was going from 0 to n, I have n plus 1 of them, right? I have the 0th one, then the first one, or the second one, or the third one, all the way up to the nth one. So I have, like, 1 to n is n of them, and then 0 is 1 more. So there's n plus 1 copies of 1 all lined up, and I'm adding them all up, so I get n plus 1. So that means this whole piece here turns into n plus 1. Which is pretty cool, because the sum symbol's gone. Right, this looks like the kind of thing, like over here, that I could maybe think about taking a limit of as n goes to infinity. Okay, so let's think about the second term now. Here, we basically have to deal with this part. The other sum rule we learned that I scrolled away from is that when I is 1 to n, adding up I, right, that means you're adding up 1 plus 2 plus 3 plus 4 plus 5. The rule was, it turns out to be n times n plus 1 over 2. Now here we're actually doing n equals 0 to n, but that's the same thing as if it's from 1 to n. Right? Because the one on the right here, first I is 1. So it's 1 plus 2 plus 3 plus all the way up to n. On the left here, it's the first thing is 0. So 0 plus 1 plus 2 plus 3 plus so those are the same thing, because the 0 doesn't add anything. So in fact, you can have I be 1 or 0, and this formula still works. Okay, so that means this whole sum on the right side can just become n times n plus 1 over 2. Can't forget to keep that fraction. And then I'll have n times n plus 1 over 2. Okay, looking good. By the way, I didn't want to talk about... so because of this thing where we can pull the over n out of the sum, we actually could have pulled this 3 over n out all the way at the beginning, instead of distributing it through. So I wanted to show off the distribution math because it's good to remember how that fraction math works. But it's totally fine to pull this out at the beginning if you'd rather. That might make it a little bit easier. Okay. So let's just cancel and simplify things just a little bit. So just notice that, so this first term is negative 3 times n plus 1 over n. And then the second term, so there's nothing that can simplify there. The next term, there's an 18 on the top and a 2 on the bottom. So I can divide that, so that's a 9. And there's also an n on the top and an n squared on the bottom. So one of those will cancel, right? N squared is n times n. So one of those n's will cancel, and there'll be one n left on the bottom. So I'm going to have 9. So that's the n plus 1 that's still here, and then all over n. Oh, cool. So I can actually combine both of these fractions because they're both the same denominator. And I'm going to get 9 times n plus 1 minus 3 times n plus 1 all over n. I could distribute the 9 through and the 3 through, but actually notice these are both just n plus 1, right? So, how many n plus 1s do I have? I have 9 of them minus 3 of them, which means altogether I have 6 copies of them. I have 6 n plus 1s, and then I'm dividing by n. Okay, so it's kind of a lot of work, but we ended up with this nice expression for the Riemann sum. Just step back for a sec. What does this mean? Right? We started here by computing our sum that was supposed to be the area under the curve for a finite specific n number of rectangles. So that's what this formula is telling us, right? This formula in terms of n is the area when I have n rectangles, right? So if I have if I have 5 rectangles, I could tell you, hey, using 5 rectangles, what's the area under that curve? Oh, well, it's 6 times 6 over 5. Whatever number that is 7 point something. 7 point something. That's the area under the curve when you have 5 rectangles. But, right, we're trying to do a definite integral. So I want to say, well, what if we had 50 rectangles instead of 5 rectangles? Well, then it'd be 6 times 51 over 50. Whatever area that is would be a closer approximation to the true area under the curve. I'm not going to do that one in my head. Maybe I can. Is this so this is approximately 300 over 50, right? Because 6 times 50 is 300. And then, this is basically, 30 divided by 5, which is about 6. But yeah, okay, so that's about 6. You could calculate this stuff too, but you know, so we had about 7, and then we got about 6. So, you know, maybe we're narrowing in on something, right? If you have a calculator, go ahead and try like 500 rectangles and see what happens. Okay, so right, we're seeing what happens as n goes to infinity. We're doing a limit. That's the point. That's the plan. So our last step here is to say, okay, our integral of our function dx, it's equal to the limit as n goes to infinity of the Riemann sum, which we boil down to be this guy. So as long as I can evaluate this limit using these like Calc 1 rules that we did before, then that's going to be the true value of this integral. How do we use those rules, right? So I'm going to give you 2 ways to think about this. Number 1 is if I just look at this fraction, it's n plus 1 over n, right? This part. Oh, well, first of all, the 6 doesn't really matter, right? One of our rules is you can pull a constant, like something that doesn't depend on n, out in front of the limit, like that. So the 6 doesn't, I mean, it's going to affect the answer, but it's not going to affect our reasoning, really. So I'm really just doing the limit of this guy. I invite you just to think about this for a second, right? What does this look like as n gets bigger? Right, imagine n's like 10. I have 11 over 10. What's the next one? It's 12 over 11. And then maybe n's like 1,000,000 or 100. And then 100 over 99. Right? Does this look like it's approaching something? Like, actually think about this for a minute if you haven't thought about it before. Maybe it's approaching 1, question mark, right? Like, how far away are each of these from 1? Here it's 1/10 away from 1. Right? The difference, right? The difference between this and 1 is 1/10. Here the difference is 1/12. Here the difference is 1/100th. So it's 1% away from 1. Here it's you know, 1/999th away from 1. So it's getting really close to 1 as n gets larger. So this is just going to be 1. So hands-on is cool. One rule you may have learned is something called maybe like end behavior, which is saying that, like, if I have like a polynomial over a polynomial, then you just have to look at the leading term. So I compare the n on the top with the n on the bottom. The rule is that if their exponents are the same, then it's going to go to 1. Right? Like if you had like n squared over, like n squared plus 1 over n squared plus 2, for example, that would also go to 1 for the same reason. And then the last thing I'll just mention maybe is L'Hopital, which you might remember. L'Hopital says if you want to do a limit of a fraction, as long as you can take the derivative of the top and bottom of the fraction, that's your limit now. Right? The limit of f over g is the limit of the derivative of f over derivative of g. Like if this is 0 over 0 or infinity over infinity. Right? So if you're doing a fraction and the top and bottom both go to infinity, then you can take a derivative. Or if the top and bottom both go to 0. So in this case, the top and bottom both go to infinity as n gets large. So we could take our derivative. The derivative of the top is 1. Like the derivative of n is just 1, and the derivative of the plus 1 is just 0. And the derivative of the bottom is also 1. So that's also 1. Or not question mark, exclamation mark. So the point is, however you want to think about it, this is 1. And so the final answer to what's the area under this curve, it's 6. And we saw the matches are sort of evidence from before. It was 7 when we had 5 rectangles, 7 point something. And then it was like a little bit bigger than 6. And then it turns out we're settling down at actually 6. Okay, so yes, a lot of work to do it all by hand, but it's kind of cool, I think, just to do it at least once or twice. Like I said, we will learn some more powerful techniques for evaluating stuff like this that's going to make all this look like almost a waste of time. But it's a lot of good algebra practice and good thinking through this sum notation. These like sum rules about like splitting it up, like we had the sum of the two terms, we split it up as two sums. This rule about pulling the stuff out in front, we're actually going to be using rules very, very similar to those when we work with these integrals, even when we're doing the shortcut method. So it's good to understand those rules algebraically before going forward. Okay, cool. So that's a good example of definite integrals. Let's move on to 4.3b. We'll talk about some geometry and properties of the definite integral. Okay, so we learned the definition of the definite integral. We're going to talk about some useful properties, shortcuts, pictures, things to think about. Mostly talking about some geometry examples. So, right, remember the whole point of what we're doing is getting the area under the curve of a function. So, if the graph of the function happens to already be making a shape that we know what the area is from geometry, then we can evaluate the definite integral, right? Like, if my function, maybe it's like y equals 2, for example, and I'm going from 1 to 5, then I already know the area of this, right? It's 8, because this is 4 wide and 2 tall. So if I was asking you to do the integral from 1 to 5 of 2, then the answer is 8. Right, 2, when I say 2 here, I mean like this function, f of x equals 2. Right, at every input, the output is 2. And I know it's 8 without doing any of that Riemann sum stuff, right? Like, I shouldn't be able to just write equals something over here. I'm supposed to be able to write, this is defined as the limit of something, right, blah, blah, blah. But no, we can skip that and just say it's 8, because I already know it's the area of a shape that I know is a rectangle. So it's a little bit cheap, right? Like, we're not really doing anything new here. We're just saying, hey, I know area formulas. But it's just good to make the connection very explicitly that, like, this integral, like, it really is the area under the curve in the sense that it's going to recover, like, area formulas that we already know from geometry. And in fact, like, these, like, geometry formulas, like, what's the area of a circle? It's pi r squared. We can actually, like, use an integral to come up with that formula if we didn't know it already. And in fact, you might think about this. Where does this formula even come from? Well, it comes from your middle school geometry class, right? But how do they know it's pi r squared, not something else? Why isn't it like pi r cubed or whatever? Again, the first time people were thinking about, like, geometry thousands of years ago, they were, like, drawing pictures. Like, here's a circle, and let's have a square that's pretty close to a circle. Let's have a pentagon that's closer to a circle. Oh, let's have a hexagon that's even closer to a circle. And they were imagining this sort of process of getting closer and closer to a circle, and they used arguments to argue that this was looking like actually pi r squared, where r was the radius of the circle. So this formula is actually fundamentally like a calculus thing, and you can do calculus in the modern sense to do this same sort of argument and come up with pi r squared. So anyway, let's look. Our main examples of this geometry connection are going to be, in fact, rectangles, circles, and also we'll look at triangles. So I basically did the rectangle example already, but let's just look at this one as like just a quick application. Someone comes to you and says, hey, what's this integral? And you're like, well, I don't really want to do a Riemann sum because that's annoying, but look, this 5 here, that actually means, like, right, f of x is 5, and it's like the graph, like y equals 5. So here it is. And we're going from 0 to 100. So the integral is the area under this curve. So what's the area under this curve? Well, I can do geometry, right? It's 100 wide, it's 5 tall, so this better be 500. So this integral is 500. So again, you don't have to do any Riemann sum stuff, you just know it's 500 because you know it's a rectangle. Okay, cool. The main point here, I think, is just knowing that the integral really does an area, so that you can do this. It's not hard if you know you can do it, but you need to know that you can do it. Also, maybe the trickiest thing is just recognizing that when I write 5 inside like that, it means this function f of x equals 5, which has this graph, right? If I have the integral of 1 dx, right, it's this function, where that's 1. I can even do integral of 0 dx, right? It's y equals 0. I'll let you think about what the area under that curve is. Okay, so that's rectangles. Pretty straightforward. We could do triangles the same way. And again, the real novelty maybe here is recognizing that the integrand really is a triangle, right? Someone comes to you with this integral, says, hey, let's do this integral. I'm like, okay, I don't really want to do Riemann sum, but let's just graph this. Y equals 4x. What does that look like? It's a graph, looks something like this. Slope 4. What are my bounds? -2 up to 1. Okay. What does this area under the curve thing mean? Well, remember, it's the area between the curve and the x-axis. So it's here, this area, plus this area. When I say plus, actually we're going to count this part as negative, and we're going to count this part as positive. Okay, but what are these shapes? Well, my picture's not great, but you probably believe me that these are triangles, right? These are straight vertical sides. These are right angles. These are right triangles, even, right? So as long as I know the area of a triangle, and I can find the base and the height of both these triangles, I can evaluate this integral. Let's just remember that the area of a triangle is 1/2 base times height. So our left triangle, let's do the left one first. The base is what? Well, it's this width. So it's 2, right? It's from -2 up to 0, so the base is 2. The height is, how tall is it? Well, we need to know this length, right? How do I know that height? It's this guy, right? I need to know what the y value is right here. How could I possibly find that y value? Well, remember, this is our function, right? F of x is 4x. How do I find the y value at a specific x value, right? This y value is hanging out just below, like it's the height of the function just below this, where x is -2. So I need to just plug in -2 into my function, and that'll give me the y value right there, below -2. So 4 times -2 is -8. So the height here is 8. But we got -8, right? Because that tells us like this is -8. But when I'm thinking kind of geometry, I'm thinking like the distance here is 8. So we can say the height is 8. Okay, so the area of the left one is 1/2 base times height. So 1/2 2 times 8, otherwise known as 8. So that's the area of the left side. And remember, we're going to count this as negative. So in our final answer, we're going to have -8 plus something, and we'll figure out that something right now. It's this other triangle. So for the triangle on the right-hand side, what's the base? Well, it's 1, right? From 0 up to 1. What's the height? Again, it's this distance. So I need to know that y value. How do I find it? I got to plug in this x value right here. So let's do f of 1. It's 4 times 1, otherwise known as 4, and our height is 4. Right, so this y value is 4, which means this total height is 4. So the area of this right-hand triangle is 1/2 base times height. The base is 1, height is 4, so that's 2. So that's the positive area right-hand side triangle, -8 plus 2. So then we get -6. So that's kind of telling us that there was more area below the axis here on the left side than there was on the right side, which makes sense from the picture, but it's good to see that. Okay, again, right, so we didn't have to Riemann sum, but we had to do a little bit of like geometry, drawing a picture. The main thing that you're going to be expected to do is, like, I see this integral, I recognize that this function is going to give me some triangles. Even if it doesn't jump out to you, just looking at the, like, 4x, that's fine, just graph it and start thinking, okay, can I break up this graph as being maybe a couple of triangles? You're going to see some problems where the graph is maybe some triangles and like some squares and maybe even some circles, and we can just do all those areas separately and add them up. Okay, so that's triangles. Let's do circles. So the circles is probably the hardest one because we have formulas which look like this, and you're supposed to remember that that's a circle, basically, right? So just remember, right, you've probably seen the circle equation, right? X squared plus y squared is r squared, right? So if I want to have like a radius 2 circle, if I want to have a radius 2 circle, let me try that again. Oval, but whatever. The right equation to write for this is x squared plus y squared equals 2 squared. So x squared plus y squared equals 4. Okay. Notice what happens if I rearrange this a bit, right? Like here, like this x squared plus y squared equals something. That's not like a y equals, right? And normally, like, it has to be y equals in order for it to be a function, like, to be like a graph of a function. This kind of looks like a graph, but like it doesn't have the vertical line test thing, right? It's not a function. So there's something funny going on. But let's just try solving this for y anyway and seeing what happens. So I can subtract x squared from both sides. Okay. I can take the square root, maybe? Okay, so that's looking a lot like this, what we had inside here. So this is legit, right? If I do y is square root of 4 minus x squared, that's like a y equals version of the circle, and this is giving me a graph of the circle. Except I lied to you a little bit. If I go on Desmos or something and graph this guy, what's going to show up is just this. This will be 2 here, and this will be -2. Why is that showing up? Well, like I said, this is not a function up here. We don't have the vertical line test. So there's no way I can have a y equals, which actually gets me the whole graph. What's happening here is that you might remember, your math teacher always says that when you take your square root, you're supposed to do plus or minus the square root, not just the square root, right? So that's maybe a more complete answer. So what's going on is that if I just do y equals positive square root, that's getting me this graph. So this is this graph. If I do y equals negative square root of 4 minus x squared, that will look like this. Which makes sense, right? It's just negative of the other one. So there's no way to get a single graph, a single y equals that graphs a circle, but I can get a pair of 2 y equalses, which together kind of make up a circle. So the main point is that when you see something like this, you are supposed to recognize it as a circle. It's not too bad, it's just any time you have square root of anything, any number, minus x squared. anything like that is always going to be the top half of a circle. The square root of 10 minus x squared, square root of 1 minus x squared. Those are all circles. You're supposed to recognize the radius of the circle. In our example, the radius was 2, and we had a 4 here. Right, this 4 came from this 4, which was originally r squared in the first place, right? So the number that's sitting inside here is like r squared. So like if I have like square root of 4 minus x squared, that means square root of 4 is 2, the radius is 2. If I have square root of 10 minus x squared, like square root of 10. The radius is square root of 10, whatever that is, right? I'd have a graph and there'd be square root of 10 right here. A little annoying, but you could do it, you know? So this guy, it's a circle at the top half of a circle because it's the positive square root. So this is the top half of the circle, and it's a radius of whatever the heck the square root of 9 is, which is 3. So this is a circle, top half of a circle of radius 3. So the graph, let's draw it a little better. The graph will be that, like that, and that's going to be radius 3. So the only real hard part of a problem like this is just you're supposed to recognize that that square root of 9 minus x squared is a circle. And they probably won't say circle, right? Okay, so that's a circle. We're trying to get the area. We already know of the area of a circle. It's pi r squared. Oh, we should mention the bounds here, right? It's from -3 to 3. So, right, like mercifully, whoever wrote this problem, which was me, set this up so that the area you're getting is between -3 and 3. You could try to do like -1 to 1 of the same function. I'd have the same graph, except I'd only be getting like this part. I'd be artificially like restricting you between -1 and 1. And that's actually not something we can really do super easily without calculus. Right? It's only because I'm getting the entire, all the way to the left and all the way to the right part of the circle that I have a hope of using my circle formula. You could also imagine trying to go like -10 to 10. Also doesn't really make sense because like it's sort of out of bounds here, right? My function is not defined for these other numbers. Right? I could try 9 minus 10 squared, like that's one of the bounds, right? So just kind of thinking like, is my function actually defined there? Well, this is like square root of like, it's 9 minus 100, right? So like -91 or something. So that's square root of negative numbers, so that's bad, right? So it's sort of out of bounds. So on these circle ones, like you're only going to see these bounds be like the square roots of this number to be actually the edge of the radius. Okay, anyway, our circle's area here better be pi r squared. We know r is 3, so the value of this integral, just because it's a circle, so it's pi r squared, pi is 3, pi times 3 squared, so that's going to be 9, except, right, this is only the top half of the circle. Pi r squared gets me the entire circle, so I got to cut that in half in order to get the actual area. So I'm going to write just divided by 2 there. So maybe as a final answer, you could say like 9 pi over 2. Okay, cool. So again, we can find the area under a curve by using a geometry formula if the curve happens to be making exactly a particular geometry shape. Sometimes it's a little bit hidden inside the graph, but if you draw the graph, you can find it. And sometimes it's super easy. Cool. Yeah, so there'll be some problems where you're supposed to connect the geometry to the integral. So I wanted to talk about that. Let's take a look at now some properties of the definite integral. So we've talked a lot about what they represent and sort of how to compute them. This word properties, in a math class, when we say properties, it's sort of like what are just like some useful rules and tricks and things that we can use, like true facts about this new thing that may or may not be useful in different situations. So there's just a bunch of them, and they're pretty straightforward, but we'll just talk through them. So the first one I'm calling the trivial interval. So in math, trivial means like kind of like edge case, like kind of a silly edge case. So what would happen if I did the integral like from 2 to 2 of my function? Like, guess what you think that should be. Well, here's my function, y equals x squared. Here's 2. I'm starting at 2, and I'm ending at 2. So the only thing that could maybe possibly happen is like an area that's like an infinitely thin slice right there. Doesn't really make sense. It should probably have area 0 if it has any area at all. So yeah, we say this is 0. So whenever you have just the same number in the top and the bottom, that's just 0. You're usually not going to like have this exact thing like show up in your algebra, but sometimes there'll be like a trick where you have to like recognize that something is sort of like this. We'll actually see that in just a second here. Okay, so that's trivial interval. I will write maybe like a generic version, right? So that C means it could be any number. F of x means any function, and it's always 0. Right? If I start and end at the same number, right? They're both C's. I said any number, but because they're both the same letter, it's the same number, right? So this means 2 to 2 or 10 to 10. Anything like that is the result is 0. Okay, next one is flipping the direction. So this is talking about if I do the integral from 1 to 10 of my function, what would happen if I tried to do like the integral from 10 to 1 of my same function? Would that like make sense? In my examples, I've kind of just been going like from left to right always. So basically, yes. You just have to think about what it means a little bit. If I do like y equals x, here's my function. If I go from 1 to 10, that's my area. I'm kind of thinking about this as like I start at 1 and I go to 10. As I go, I'm like accumulating more and more area as I go to the right. So that's kind of what the original is doing. It turns out a useful way to think about what the second one is doing is sort of symmetrically. Since I'm 10 at the bottom, I'm like starting at 10, and I'm moving towards 1, in fact, instead. So I'm kind of going from right to left instead. And perhaps I'm sort of decreasing the area as I go, instead of increasing it. In the sense that if I start at 1 and I go up to 10 and then I go back to 1, I probably should be like at 0 or something. That's sort of the motivation for saying that this is just negative. So if I integrate like from left to right, I get a positive number, if I'm above the x-axis. And if I integrate from right to left, I get the same number but negative. So both this flipping and trivial are sort of like conventions which make sense and also play nice with this third thing, addition. And this addition one is the one that we sort of like really want to be true. It's like maybe the most obvious and important one. And these two are sort of necessary consequences from making addition work out. So let's think about addition. I'm just going to write the rule. So if I go from a to b of some function, and then I add on another integral, which is going from b to c of some function, then this is going to be the same as going from a to c. Right, so just like picture, like, here's my function, here's A, here's B, here's C. If I integrate from A to B, that's that area, then I'm going to integrate from B to C, that's that area. So it better be the case that integrating from A to B and then integrating from B to C is like the same in total as just integrating the entire thing from left to right. So that's what this rule is about. If I go part of the way there and then finish, that's the same as having gone the entire way from the beginning. So I'll write that sort of generic version. A couple things about this are a little bit funny. It turns out that, so just first of all, notationally, just notice that like these match, right? Like A goes to B, B goes to B, B are the same, and then B goes to C, right? It's important for those to sort of line up. And then the other thing that's kind of funny about this is, or the thing that's kind of funny about this is that actually this B, like in my picture, we had B like in between A and C. But it turns out B actually does not have to be between A and C. B can actually be anything, and it's still true. So, like for example, if I wanted to integrate like from 0 to 1 some function, it's actually the same as if I integrate it from like 0 to 100. And then integrate from 100 back to 1. Right, so I can actually pick any number I want in that sort of middle slot. And it's sort of like saying, like, you know, if I want to get from point A to point C, I can pick any other point B out here. First go from A to B, then go from B to C. But like that still works even if B is wherever I want, right? That's sort of the idea. It's not the biggest deal in the world, but sometimes that's like an algebra trick that you're supposed to do. We will see pretty soon there's a specific algebra trick that we do often. Okay. Also, I'll just not comment, like notice that like how this addition rule sort of interacts with these other two rules. Right, like this one, for example. Because of the addition rule, like if I go from, you know, 2 to 2 of my function, right, say x dx, because of the addition rule, that better be the same as like going from 2 to 0 plus going from 0 to 2, right? I can pick whatever I want in there. I pick 0, just like for example. But like, I know that because of the trivial integral rule, this is supposed to be 0. And now I could like rearrange this, right? This guy plus this guy should be 0. So I could subtract, you know, 2 to 0 of my function. I should subtract the other one over. Is minus 0 to 2. Right, so these kind of are playing with each other in ways that make sense. I should mention also, like when I say properties, like I say, like when I say that this is true, that like these are equal, like it's sort of just on my authority, but like what it means is like if you go back to this definition, right, if we go back here and say what is the symbol on the left mean, it just means the thing on the right. Like this is like the programming engine guts of like what the thing on the left means. It just turns out if you start writing down like these sums and these flips and stuff that we were just looking at, you can translate those into this thing on the right, this engine code machinery on the right, and just like see what pops out. And you can prove that what pops out is these kind of right hand side stuff, these rules. Right? Like what would, like, you know, like what is this, right? Well, turn this into the Riemann sum thing, turn this into the Riemann sum thing, and then do a bunch of annoying math and algebra, and it'll turn out that this is what comes out on the right side. So that's what, like, kind of what I mean by properties, like sort of interesting things that you can prove from what you start with. This class is not about proving those things, but about using those things. Okay. So there's a couple more here. Okay, so I made a slight mistake here. So this thing that we've been talking about, I realized I actually labeled it this weird phrase, break into 2 at C. I got confused because there's a plus here, and so addition. But I actually meant for this break into 2 at C to be referring to this rule here. So sorry about that, that's confusing. The addition will be something slightly different, which I'm going to bring down here. So this is just the names, it's not that big of a deal. So what is this addition, the addition rule? So that's much simpler than this breaking into 2 pieces thing. So what this addition rule is in fact just the same addition rule that we saw with the sums. If I take any integral that I like, except I happen to be adding 2 functions inside, that's going to be the same as doing the integral of the first function plus the integral of the second function, and it's over the same bounds. Right, so for example, like if I integrate like 0 to 3 of like x plus x squared, that's going to be the same as integrating from 0 to 3 x plus integrating from 0 to 3 x squared. So I can like distribute the s, the integral sign, like across both the terms, just like we did with this sigma, the sum symbol from before. And in fact, this is true basically because it's true for the sigma. So that's a really useful, powerful rule, and we actually use it all the time. Never forget that you can do this. It's really, really common for Calc 2 students to like totally know how to do this one and totally know how to do this one, but then they like, oh, I don't know how to do this one. So you do know how to do this one. It's you break it up into the 2 things that you'd know how to do. Super common rule. Okay. This scaling one, I would kind of group together with this addition one. A simple algebra thing that you can do that's similar to what you can do with the sums. So if I ever have an integral, and I have like a number, c, so c is just some number, times your function, as long as this number doesn't depend on x, like it's just a number, like 2 or something, you can pull it out in front. This is times. C times your function. Right? So like for example, if I have like integral 0 to 1 of 2x dx, it's the same as 2, 0 to 1x dx. That's very similar to one of our sum rules from before. Something I'll just mention about this scaling rule also is that don't forget about fractions, right? Again, there's a lot of Calc 2 students who are like, oh, maybe like I know how to do integral x dx, but all of a sudden I have no idea how to do this one, integral x over 2 dx. It's like, yeah, you do. If you know how to do this one, then you do know how to do this one. Because, right, x over 2 is the same as 1/2 times x. 1/2 is just a number. Because of our scaling rule, we can pull that number out front. So a lot of calculus is about this. It's starting with something that you're maybe not sure about, doing a couple rules to turn it into something simpler that's made of pieces you know what to do with. So if you knew what this thing was, this one's just 1/2 times that thing. Even kind of scary looking fractions, right? Like, even if it's like something like this, right, you can pull both the pieces out. Right? So always keep that in mind. Okay, so that's scaling and addition. Oh, I also just mentioned, you might remember that the same thing works for derivatives, right? You might remember, like, if I do the derivative of like x plus x squared, it's the same as the derivative of the first thing, plus the derivative of the second thing, right? So that's sort of the same rule. It sort of distributes across both things. And if I do the derivative of like 2x squared, it's 2 times whatever the derivative of x squared is, right? So these are the same rules that are happening when you take a derivative as happening when you do the integral. So so that's a way to remember that. Like if you're already kind of used to doing this, right? I say how do you do the derivative of x plus x squared? You're like, oh, it's 1 plus 2x, right? And you don't even think about it, but you're really using this rule. You're doing the derivative of each piece separately. So you should think of integrals as this working the exact same way. Okay, so let's see an example of a kind of problem that's typical that you will see involving kind of using these rules. So this says, we'll say something like, suppose that we know these integrals already, right? Again, f is some unknown function. I have no idea what it is. But I'm told, just as an assumption for the sake of the problem, whatever that function is, its integral from 1 to 6 happens to be this number 5. So a mystery function, but when I integrate it, I end up with 5. If I have that type of information about a couple different functions, then I can actually use these rules from above to sort of piece together some information. So here I have another integral. It's the same function. It's the same f. So again, my same mystery function, except this time I'm integrating it from 1 to 4, and I apparently get 8 when I do that. And now this third one, it's a new function. It's important that it's a g instead of an f. This is a second mystery function named g. What do I know about it? I know that when I integrate it from 1 to 6, I apparently get negative 3. Okay, so how can we use this information? Well, I can basically use those rules to like combine these into new things. Like for example, I could say, well, what's like f plus g from 1 to 6? Well, based on my sum rule, it's 1 to 6f plus 1 to 6g. All right. So like I can make new things from the old things using the rule. So on this problem, we're kind of going to be asked to go backwards. So let's look at this one first. So I want to integrate from 4 to 6 of 2f of x. So first of all, let's just deal with this 2, right? I can pull the 2 out front. That's my scaling rule. Why would I want to do that? Well, there's no 2's anywhere on the insides of these integrals, so probably I need to like isolate this part and work with that. Okay, how can I deal with this? It's from 4 to 6. I don't have a 4 to 6 up here, right? So what do? Well, I don't have a 4 to 6 specifically, but I do have a 6 and a 4. And in fact, those are both connected to 1. So this 1 is like a third number that both 4 and 6 are connected to through that integral sign. One of our rules was about if I have this like third in between number, right? A, C, B. B could be anything. I can get from A to C as long as I go from A to B first, and then from B to C. So, like, if I go from 1 to 6 with f, and then go from, well, what can I do, right? We said that, like if I'd have to put a 6 here to match the rule that we had before, right? What's this b got to be? Our third number, which is attached to both of them, has to be this 1, this extra 1. So that's not the idea we want. We want to have like 1 to 4. This 1 wants to be our b, our third number. And I want to have I want to have 1 here so that those match. That was our rule from before. Which means I'd have to have a 6 here maybe. But I have 1 to 6, not 6 to 1. Oh, there's that other rule we had, right? Which said that I can flip the order from the top to the bottom as long as I add a negative sign. So, let's just put this together. So our integral here, so it's 2 times something. What can I do? From 4 to 6? 4 to 6 is the same as, let's go from 4 to 1 with my function, plus let's go from 1 to 6 with my function. That's using the breaking up of the middle rule. I know that 1 is a good, well, I could pick 100 as my in-between b number. Why do I want to pick 1? Because 1 is involved up here, right? Now, what can I do? 4 to 1, I want 1 to 4. I can get that by flipping the sign. 4 to 1 is the same as 1 to 4 as long as I put the minus sign there. And then the other one can stay. That's plus. That's fine. Sorry, it's a little messy. It's a plus. And now we have something we can work with, because like this chunk is 8. Like that was our given information. This chunk is literally just 8. And this chunk, this 1 to 6 chunk, that's literally just 5. Like take this equal sign seriously. So I can replace it. So it's negative 8, and then plus, this is just 5. Okay, so 2 times negative 3. So apparently that integral ends up being negative 6 by combining this information from the f stuff we were given. This is probably the hardest one. This idea of like, I take the 4 to 6, I got to break it apart into 4 to 1 and then 1 to 6. Again, I would think of 1 in particular, of all numbers, to break it apart at, because I have 1 connected to 6 and connected to 4 here. Okay, just a couple more. Let's take a look at this one. So this one's pretty straightforward. I have 1 to 6, f, g, 1. I have 1 to 6, f up here. I have 1 to 6, g up here. So probably I can just start breaking this apart, and it's going to work out. Remember, I have the plus rule, the addition rule. If it's the integral of a bunch of things added together, that's the integral of the first thing, plus the integral of the second thing, plus the integral of the third thing, all with the same numbers. 2 things I want to mention here. Right here, I've been writing just f dx. I should be writing f of x dx, but I'm lazy and just writing f dx. It's okay to just write f dx as long as you know what you're doing, but it's short for f of x dx. I don't want to forget that f is a function of x. And I really, in particular, I really don't want to start like thinking that f is like a number and then start pulling the f out front. No. F, it's just short for, like, it's really like, you know, x squared plus 1 or something. I just am not committing to what function it is. So yeah, it's okay for short to write f dx, but you should probably write f of x just to remember that it's actually a function of x and sine. Okay, and then the other thing to mention is, what is this, right? Like, we don't have information about the integral of 1 dx. Except we know how to do the integral of 1 dx. The integral of 1, right? What is, right, I think of what's the graph. What's y equals 1 look like? It looks like this. I'm going from 1 to 6. The integral means the area. Oh, hey, that's a rectangle. Its width is 5, its height is 1, so that better have area of 5. So even without like anything else, doing Riemann sum or anything, I can just figure out on my own that the value of that is 5. The values of these two are coming from the given information at the top. So f from 1 to 6 is 5, g from 1 to 6 is negative 3. So we add all this stuff up. We should get 7, I think. So sometimes it's a combination of using maybe the given information, and then sometimes like figuring out an integral using, for now, geometry or Riemann sums. Very soon, there will be other ways to do that integral as well. Cool. The main logic here, right, point of this example was using these various rules, breaking it up with a third middle number, c, scaling, addition. And we didn't actually end up really using the trivial thing, but we did use flipping the direction. Okay, so one more topic in this section, finding the average value of a function, and then we'll do a little bit of a summary of what we've learned so far. So one nice application of integrals is average value. So this is not going to be like an obviously geometric application. It's going to be kind of a physicsy, more abstract application. But it's something we can do with an integral. So first of all, let's think about what do I mean by the average value of a function. So in this example, it says a car is moving with a velocity function, v of t is 1 minus t, on the interval 0 to 3. What is its average speed? So first of all, like, what does average speed even mean, right? I could, if I'm driving, I could drive at constant speed the whole time. That's one possibility. If I was going 20 miles an hour the whole time, my average speed would be 20, right? Maybe for the first half of my trip, I go 40 miles an hour. And then the second half of my trip, I go 20 miles an hour. Then I would have a new average speed, which would be like 30, I think, right? In between the 20 and the 40. I could do something even different, right? I could first go 10 miles an hour, and then go 20 miles an hour, and then go 50 miles an hour. And if I did this all for the same length of time, then I could figure out the average, right? It'd be like 50 plus 30 plus 10, which is like 90, and then divide by, maybe that was over 3 hours, average 30 miles an hour, or something like that, right? So it's like, over the course of the trip, for sometimes I was going some speed, sometimes I'm going another speed. I kind of average that out. We can think about that also if my velocity function happens to be like curvy, right? Those examples I was sort of saying out loud were sort of like, first that's my velocity, and then I jump, and we sort of averaged like these y values. But I can also imagine having some curvy velocity function. So sometimes I'm going faster, sometimes going slower. Actually, let's do that example. Maybe sometimes I go faster and sometimes I go slower. But what should like my average speed be? Well, it should be like, right, if I'm going fast for a long time, that should pull up the average. If I'm going slower for less time, that doesn't affect it as much. So it's like something like, maybe this? Like maybe that's my average speed? So we're kind of going to be thinking of average speed, right, as the sort of most in-between-ish y value over all the y values. But it's sort of weighted by how long you're doing it, right? So it's a little hard to pin down that without doing like a zillion examples, but you can imagine, if I'm going flat the whole time, that should be my average speed. If I'm going like this, if I'm doing a constant acceleration, maybe, my average speed should be like right in the middle, something like that. A good way to think about average speed is like the speed that, if you were going that speed the whole time, it'd be the same final result as whatever you were doing instead, right? If I'm driving from Corvallis to Portland, it takes me 90 minutes, and say I go on average 60 miles an hour. If I go on average 60 miles an hour, that means it takes me 90 minutes, right? If it's 90 miles, say. But sometimes I'm going faster, sometimes I'm going slower. But if whatever speeds I actually went, forget about those. I got there in 90 minutes. 90 miles an hour, or sorry, 60 miles an hour, is the right speed at which, if I just stayed at constant speed the whole time, I would get there in that same amount of time, right? And you can picture that as a graph on here, right? Where I'm not doing speed anymore. I'm doing position or distance here. Like my position, right? Maybe I'm going, sometimes faster, sometimes slower, and my speed is sort of like slopes along here, right? Sometimes I'm going faster, sometimes I'm going slower. But if I did like this average speed, like from the beginning to the end, kind of ignoring the up and down bumps that I'm doing, I'd get there in the same amount of time. So that's another way to think about average speed. So anyway, what I want to think about is what the heck this has to do with an integral, right? So here's my idea. What does the average of a bunch of outputs of f look like? Right, so I'm not doing an average of maybe like all the values of f, because that's a little hard to think about. But let's just do a sample. Let's just grab some of the values of f, right? In this story, v is 1 minus t, so my velocity function looks something like this. I'm going on the interval from 0 to 3. Notice that 3 is going to be like this, I think, because at time 3 you have negative speed, -2. So you're going all the way to here. So let's just sample some outputs, right? Let's say, what's my speed at the beginning, what's my speed at the middle, and what's my speed at the end. Right, at the beginning, v of 0 is 1, based on the formula. At the middle, which is, say, 1.5, my speed is, well, 1 minus 1.5, so negative 0.5, which means my drawing here was not accurate. Sorry about that. 1.5 is actually like right here. I want these to be evenly spaced, is why I picked 0 and 1.5. Let's also check v of 3. 1 minus 3 is -2. So here's 3 outputs, right? These 3 outputs. So let's just average them, right? I'm thinking about the average output. So here's 3 outputs. Let's just average them, right? How do I average? I add them up. V of 1.5. I add them up and divide by how many there are. I divide by 3. And I can do the math. I guess let's just do it just for this one example. Plus -2 divided by 3. So it's 1 minus 2, so -1, minus another 1/2, so -1.5 over 3, which is like -1/2. So like my average velocity over that interval, at least when I sampled 3 points specifically 3 points, that gave me an average velocity of -1/2. Okay, right, but that can't be my sort of actual average velocity, right? What if my had more ups and downs and stuff? Like in this case, I think it's because it's a straight line, it's not going to matter. But like theoretically, I want to be more accurate than sampling just 3 points. Like I want to sample lots of points, right, to get my average velocity. So we can imagine maybe we do 4 of them instead. We do v of 0 plus maybe v of 1 plus v of 2 plus v of 3. Maybe I grab 4 outputs. I'm not going to compute them this time, but just imagine grabbing 4 outputs, adding them, and dividing by 4, and I get some number. But maybe that's not good enough. Maybe I want to take, maybe I want to take 5 outputs and divide them by 5. Or maybe I want to take 6 outputs and divide them by 6, right? So we are sampling at more and more values that are spaced apart, more and more close to each other, and dividing by n, by a number that's getting larger and larger, and sort of taking a limit. Right, so if you write this down carefully, what's going to happen is you're basically writing, let's do the limit as n goes to infinity of, well, what's this thing? The thing at the top is a sum, right? It's a sum as I goes from 0 to, something. It's my velocity of, well, here's 0, 1.53. That's like x0, x1, x2. But then when I go to more n's, I have x0, x1, x2, x3. So I'm sampling these xi's, which are also depending on n, but I'm getting more and more of them. Like, that's my spacing of the points I'm sampling. And they're all, I don't know, maybe, or I did not explicitly multiply by like a width here, except I did do this like dividing, this dividing by 4 thing. So if I want the, so if you work this out, what happens is that the top, when I'm adding up these values, right now I'm just sort of like weighting them with like a 1, because I'm imagining like multiplying by each of them by 1 in order to get like this average, this total. But this top part really sort of turns into a integral on the top, adding up a bunch of values. In order for that to like make sense and end up being the area, you have the delta x, and it works out. So this top part is basically becoming a integral. However, when we're doing this average, we are always having, we have divided by 3, divided by 4, divided by 5. We're basically taking this whole sum, whatever that top thing is, and end up dividing it by n. So again, we're kind of skipping the details of exactly how you derive this, but the point is that we're adding a bunch of stuff and dividing by this thing that's getting bigger and bigger. That kind of feels like the same Riemann sum thing that we were doing before, and in fact we can say that we get like an integral here. So the official way it's written is going to be on the next page. So you can kind of take this as a definition, if you like, of what average value means, or you can think about this Riemann sum we were doing on the last page. So the average value is just the integral, right? Like, this is just the regular integral, except then I divide by something. Or multiplying by a fraction is the same as dividing by, right here, multiplying by 1 over b minus a is the same as just dividing by b minus a. So you could totally write this like this. It's exactly the same thing. This is just more common for some reason. What's b minus a? Well, it's got to be the width of that interval, right? We're going from a to b. B minus a is just how wide this interval is. By the way, where I was kind of skimming over this part up here, remember, like, delta x is like b minus a over n. So if you think about like this dividing by n thing, you could think about how that would end up putting this b minus a thing on the bottom. So I'll let you think about that. So right, basically what you need to know is that if you have a story problem that says find the average value of a function, then we're just going to do the integral, but then we're going to divide by the width, a to b, b minus a. So for our car, I think it was v of t is, it was t minus 1 minus t, right? Yeah. So v of t is 1 minus t, and we're on the interval 0 to 3. So we have our car. We want to find, we're going to find the area, right? My average value, which, by the way, sometimes they write it like this, f average. It's kind of a non-standard notation, but you can write that if you want. So it's just going to be 1 over b minus a. Well, this is a and this is b. So b minus a is 3 minus 0, which is 3. So then that's just the width of the integral, right? So it's 1 divided by 3. And then I just do the integral from 0 to 3. F. Our particular function is v, which we know what v is. It's 1 minus t. Cool. So as long as we can get the value of this integral, then our final answer is just that number divided by 3. One thing I should mention here, which because I don't think we've talked about it yet, my function is a function of t, and so in my integral here I have a t, and I also wrote a dt. So like this dx thing, it's really like this x is, it's like brackets like I was saying, and it's also sort of reminding you what the variable is. So if you have a function of x, it should be dx. If you have a function of t, it should be dt. And you can have other stuff, like you can have integral of y squared dy. That's fine. You'll see that sometimes. Okay, so we can find the average value. We just got to find the value of this integral. How could we possibly do that? Well, these are some triangles, right? We talked already about how to find the value of the integral, given that you know it's like triangles, or some other shapes. I think we got to figure out what this breakpoint is and what these heights are in order to have like a final answer. So let's just think about these triangles. What are these coordinates? How could I find that x coordinate? Well, I got to figure out what the t value is when the y value is 0, right? Because that's the thing that will get me my crossing right there. So I just have to solve this. Okay, so that's time 1. We already know this is 3 and this is 0. I want these heights, so let's just check the height at time 0 at the beginning. That's 1, so my initial speed is 1. And let's check the height at the end. We know the end is 3. So I already know this is -2. I think we did that math earlier. So that height is -2. So we just need enough info to get the areas of these triangles, right? Now I know that the left one is 1/2 base times height. The base is 1, and the height is also 1. So I think we end up with area 1/2. And the triangle on the right, 1/2 base times height. The base is 2, because it's 1 to 3, right? And then the height is also 2, because we figured out that this y value was -2. So that's a total of 2. And we'll just add these up. Remember that we're going to count the left one as positive and the right one as negative, because the right one is below the axis. Okay, so in the end, my average value is 1/3 of what? 1/3 of this integral, which is the left triangle plus the right triangle. The left one is positive 1/2. The right one is -2. So whatever that number that turns out to be is our actual average speed. You can go ahead and just work it out. So 2 is, I want to turn into halves, right? 2 is 4 halves. So it's 1/3 of 1 minus 4, it's -3 halves. I can multiply the 1/3 in, but it's going to cancel with that 3, right? So we get -1/2 in the end. So on average, they were going -1/2, and you can kind of think of that as like here's -1/2, maybe. That was sort of their average speed, their average y value. My picture's not super great, probably, but right, because we know this triangle is bigger actually because the height's 2, so it probably looks something more like that, maybe. And so like their average speed, like they spent a little more time below the graph, so it kind of pulls that average speed down. Okay, cool. So yeah, average value, we use this formula. It's basically just the integral, and we divide by the width. It's useful sometimes, just kind of big picture, philosophically, to think of the integral not only as area, but as sort of like an averaging process. that's a way people think about it in physics a lot. One other thing maybe I'll mention is that if we think about, maybe I should have mentioned this earlier, but if we think about, I have the function doing something, the average y value of the function is maybe something like this. What is the integral, right? The integral is this area, right? It's the area under that curve. I want to imagine drawing a specific rectangle down here, which is this one. Okay, so like if this is the average value, this is the width, b minus a, down the bottom here, right? So what's this red rectangle? What's the area of it? Well, the area of the red rectangle is the width on the bottom times whatever that f average value is, right? It's just the area of that rectangle. So essentially what this formula, right, and then notice if I just claim, just in quotes equals for a second, suppose you believed me if I told you that red rectangle had the exact same area as the integral. Right, so this side is the black shaded part. Right, it's the area under the curve. The left side is the red shaded part, the area of that rectangle. So, like the claim that this left side is equal to the right side is the same as claiming that this rectangle, in fact, has the same area as the area under this function. So I think that's plausible because, like, if the function was like going faster or something, my average value would maybe be here, and it would get, the average would get pulled up, right? So the area of this rectangle would get bigger as the area of this background area under the curve is getting bigger as well. I kind of picture this as like a sloshing, right? If I think of the function as like doing this, if I kind of restrict it to here and imagine that area as like water and just let it slosh into this rectangle, I can maybe believe that that rectangle has the same area as the original integral. So the content basically of the average, like proving that the formula, average value formula works, is proving that basically that this really does match. Like the parts here that are like above the rectangle like really match with the parts that are below the rectangle. Yeah, so that's a cool way to think about it. Like, notice, like I didn't really say this yet. Notice I can rearrange this, right? If I believe that equation, I can just divide the right-hand side by b minus a, and now that's my average value formula, right? So the average value formula is the same thing as saying that the average value times the width is in fact the same area, that the red is in fact the same area as the black. Okay, it's not really proof, it's just kind of a nice picture. Okay, so to summarize section 4.3, what have we seen? And also a bit of 4.2. We've seen a bunch of things which are maybe new in this course. We first talked about just sums in general, accumulation. The idea that if you start with a velocity function, or any like rate of change of something function, you can compute the total distance traveled over small intervals and add them up to get a total change in distance. That was this picture where if I know my speed at every point, I can kind of recover my total displacement, my total change in position. And we kind of thought about that as like a graph, right? This is like my speed, and like, oh, over this time I went so far, over this time I went so far, over this time I went so far, and kind of add that all up to get my total displacement. That idea works not just for velocity, but sort of any rate of change function. We can do this. So any like velocity came from like the derivative of position. So whenever a function is the derivative of something, we can do that. We'll see a lot more about that very soon when we talk about fundamental theorem of calculus. This rectangles thing was just an approximation for some specific number of rectangles, but you can do more and more rectangles to get a more accurate sum. We kind of like formalized that idea into this Riemann sum idea, where we said, just let's take a function, let's chop the area under the curve into rectangles, write down carefully exactly what the heights and widths of all these rectangles are, write down a nice notation for adding it all up, and that's an approximation for the area under the curve. The thing to do is to just take that idea, but do more and more rectangles. And so we talked today about, let's do the limit of that process. So do more and more rectangles. Each time you have more rectangles, you have a better approximation of your area, and you sort of say, in the end, I have the true area. That true area we called the definite integral, and we write it this way. The definite integral from a to b of a function, and that's always just the area and the full area under the curve, no approximations. But it's sort of made up of doing a bunch of approximations. A big part of this class is going to be evaluating things that look like this. So far, we know how to find the limit of the Riemann sum, so that's kind of the long example we did earlier today. It's kind of hard, and it only works if it's a special sum. I didn't say too much about this before, but like we really relied on those formulas, right? Like the algebra had to happen to work out so that we could do this thing, right? That's not always going to work out, right? If I just take some random function, I'm not necessarily going to have I show up. That only worked in our example because because we specifically chose the function for it to be nice. So we can always do that, but it's kind of hard, and it doesn't always work. I mean, we can always try, but it doesn't always work. Something else we could do, which we didn't talk about too much, but you can just estimate the sum for large values of n. Right? So this is what you do probably in real life. You just have data. Right? In real life, you might have data which looks something like a function, but you don't have like a formula for it. You can still do the Riemann sum, the rectangle idea, right? Given your discrete data from real life, you can still do the rectangles thing and get a number for the area, and that's it's a good approximation if kind of pretending your data came from a function, right? You can even do this if you have a function, right? If a function is like too hard to do the Riemann sum thing, you can still like do samples of it, even if it came from a real math function. Okay, so that's not great, right? Estimates and special cases. We did have like a perfect case, right? If we already knew that the function was representing some specific area, like a circle, we knew it was a circle, or we knew it was a rectangle, or we knew it was a triangle, then because I know the geometry formulas, I can find an exact number for this. So again, sort of only if you already know the answer, sort of, right? So also not great. So what would really be great is a better way to actually compute it, and that is the plan. So so far I just want us to be like familiar with these ideas of the areas, the rectangles, approximating, knowing what it has to do with something like velocity, and those kinds of things. So there's a whole story about sort of the better way to compute it. That's for next lecture. A little bit of a preview. There will be derivatives involved. There will be this thing called accumulation function. There will be a thing called the fundamental theorem of calculus. So we'll get there. That's going to allow us to sort of circumvent these limitations and do it for real. Okay, thanks for watching. I will see you next time.